Well, will you look at that? We are already in chapter 6 of the dark art of linear algebra. This chapter is all about changing bases, and to make sense of that general topic, we need to begin by discussing the very simple idea of coordinates. By now, you are used to the idea of a linear map transforming everything in a space. But sometimes it is useful to think of a space in which everything remains fixed, all the points and lines and vectors and so on and so forth, but in which the grid transforms underneath them all, like a ghost just passing through everything, and that all that is changing are the coordinates of points relative to that ghostly grid as it moves around. To explain this idea further, let's consider the same vector v 3 times over. I've drawn it separately in 3 different places so that I can think about its coordinates relative to 3 different bases. In the first case, I have drawn the standard basis vectors e1 and e2, more familiarly known as I hat and j hat, but I figured I would give these more formal names to make sense of the symbol we usually use for the standard basis, which is a stylized e. I guess the way I write it looks a little bit like an epsilon, but it is just supposed to be a fancy capital E. Anyway, if I asked you for the coordinates of vector v relative to the standard basis e, I suspect you would know already exactly what I mean. We know that every vector in the plane is a unique linear combination of the basis vectors. That's what it means to be a basis, after all. So that means starting from the origin, I can reach the tip of that vector by taking a certain number of steps in the direction of the first basis vector and a certain number of steps in the direction of the second basis vector. And in this case, it looks like maybe we would take 2 steps in the direction of the first basis vector and then 2 more steps in the direction of the second basis vector. So the coordinates of vector v relative to basis e, we would say, are 2, 2. What I need to introduce now is a little notation for expressing that kind of idea. What we do is we write the vector v and then we enclose that symbol in square brackets with a subscript telling us the basis we're working with. The brackets tell us we are interested in the coordinates of vector v, and the subscript tells us the basis with respect to which we are giving those coordinates. So now we could say that expression is 2, 2. Note the distinction between plain old vector v and this thing, which is v's coordinates relative to basis e. The vector itself is just a geometric object. Its coordinates relative to a particular basis is a stack of numbers, and those numbers will change depending on the basis, even though the geometric object remains fixed. To see what I mean, let's move over to our second case, where we will have a different basis for R2. I'm calling those basis vectors A1 and A2, so naturally I will refer to the basis as a whole, A. And again, that's a very stylized capital A, easier to do when typing than when writing. So you may hear me refer to it as fancy A or crazy A or something like that. Anyway, it's an honest-to-God basis, of course, and we can discuss V's coordinates relative to that basis. What will they be? Well, in this case, it looks like we can get from the origin to the tip of v by taking 1, 2, 3 steps in the direction of the first basis vector, a1, and then once we've taken those 3 steps, taking a single step in the direction of a2, the second basis vector. So that means that the coordinates of v relative to basis a will be 3, 1. This is the exact same vector that we were dealing with before, but the coordinates are very different than they were, which is no surprise because the basis is so different in this case. In a sense, we are distinguishing between the thing itself, the vector, and the language we use to describe that vector. It's as if I want to refer to this large, flat, wooden object next to me, which you can't see, but I can thump it here with my hand. It's a real thing with existence of its own. It goes on existing whether or not I'm here, or whether or not I call it anything. But what I call it depends on the language I'm using. If I'm using English, I'll call it the table. If I'm using Spanish, I'll call it la mesa. But I think you get the point. To drive it home a little further, let's consider a third basis, which I will call b. And once again, we can ask for vector v's coordinates relative to basis b. So we have to think about how many B1 steps we would take and how many B2 steps we would take to come up with vector v. Well, it might help to think about the grid determined by this basis, which would look something like this. You'll have to forgive my bad drawing. Thinking of that can help us visualize what the coordinates of v would be relative to basis b. This is vector b1, so it looks like we're going to have to take some negative steps in the b1 direction, and then since this is vector b2, we're going to have to take some negative steps in the b2 direction. Ultimately, we will be moving in this direction, so maybe drawing a line parallel to that direction through the tip of vector v will help us see what's going on. If we take my terrible drawing at face value, it would look like we are going from the origin, something like 1, and then maybe, let's just say, another 0.8 steps in the negative b1 direction. So let's say minus 1.8. And then from here, 1, 2, let's say 3 steps in the negative b2 direction. So that my coordinates would end up being something like minus 1.8, minus 3. All right, so that is the idea of coordinates in a nutshell. And of course, there was nothing special about doing it in R2 as we did in these cases. We could have the same kind of discussion in R3, R4, R5, or whatever. Take a vector in one of those spaces. Its coordinates depend upon the basis we use to describe it. And what we will start to see in the next video or the next section of the book is that in many situations, choosing some other basis rather than the standard basis will lead us to greatly simplified descriptions, not just of vectors, but of linear maps themselves, of the matrices that represent them. And a theme we will see carried into chapter 7, for example, where it will become very prominent, is if we are given a particular linear map, we would like to figure out which basis we should use to make the matrix for that map as simple as possible. But as I say, that's to come. In this section, we're just worried about the basics. First, what coordinates are, and I think you have that idea. Then, something which is much less obvious. We want to discuss the problem of how we translate between coordinate systems. We will get to that issue soon. But first, I have to tell you something, a little technical result, important though, about this notation we are using. If v and w are vectors in some vector space, and fancy b is some basis for that vector space, then two equations are going to hold. First, if we add vectors v and w, and then take the coordinates of their sum relative to basis b, we will get the exact same thing that we would have obtained by first taking the b coordinates of v and w separately, and then adding those together. So whether we add and then take coordinates, or take coordinates and then add, the result is the same. That's the first of the two statements. And I will bet you can guess the second one. It says that if we start with a scalar multiple of a vector, and we take its b coordinates, the result will be no different than if we had first taken the b coordinates of the vector, and then scaled the results. These two, of course, are linearity properties. They tell us that this operation of taking the coordinates relative to a basis preserves vector addition, and it preserves scalar multiplication. It therefore preserves linear combinations in general, and that's the sort of thing we like in linear algebra. We'll put this to use in a moment, but first I should say a few words about why these linearity properties are valid. In the book, I write up an algebraic proof, and that's well worth going through because it gives you some practice with thinking about what is really meant by coordinates relative to a basis. It's good to look at that formal argument and be sure that you understand it. But informally, you should be able to see why these things hold just by using your basic geometric intuition. I will try to give you a nudge in that direction, but I think it will help if I clear out some space and make a little room for myself. So, let's concentrate on this first part of the claim. I'll draw some pictures down here to try to stimulate your imagination a little bit. Let's suppose we are working in R3, and so we have a set of 3 basis vectors. Now, suppose that we have a couple of vectors in R3, which we're calling v and w. Now, I think I can get you to see why this statement holds just by thinking about what the various symbols mean and what those would correspond to geometrically. Let's start with this symbol right here, which represents vector v's b coordinates. coordinates. We can think of V's B coordinates as a set of marching orders. If we are in the army, and for God knows what reason, we are constrained to move only in the directions given by the three basis vectors, but we want to advance from some point in such a way that our displacement will be as if we had marched along vector V, then we can follow the marching orders given by those coordinates, and we know that we will get there, because those coordinates will tell us something like move a certain distance along the direction of B1, then move a certain distance parallel to the direction of B2, and then finally move a certain number of steps in the direction of B3. And where will we end up? Exactly where we would be if we had simply followed the direction of vector V itself. Now look at this symbol, W's B coordinates. That too we can think of as marching orders that will move us going only in the directions given by the three basis vectors, but those marching orders will take us from any point to another point by a three-stage path, but the net effect will be as if we had just followed vector W. So we're going to take a certain number of steps in the B1 direction, and a certain number of steps in the B2 direction, and a certain number of steps in the B3 direction, and we will end up with a displacement exactly what it would have been if we could have just followed vector W itself. Okay, now think about the entirety of the right side of this equation. What does it correspond to in terms of our marching orders story? Well, that would be a situation in which we carry out two sets of orders successively. Starting from whatever point, we carry out these marching orders. Those will take us ultimately from our starting point to the tip of V if we had tacked V onto it, and then we add on another set of steps, another set of marching orders. We move only in the directions given by the basis vectors, but their net effect is to move us one full W step. So we end up at a point like this. But that point, of course, corresponds to the vector V plus W, because we've simply added V and W, tip to tail, and we got there by following first V's marching orders and then W's marching orders. But of course, we could have done the exact same thing by following the marching orders relative to basis B for the sum V plus W. And when you think of it that way, I hope you see that this property really is pretty obvious. And I will leave it to you to think about this second one in the same way. You'll see that it is pretty obvious too. And of course, you should also look in the book where, as I said, I give an algebraic proof, because as I've said dozens of times now in this series, you want to be able to switch back and forth among different perspectives. That's how you end up learning this subject. I mean, this chapter in particular literally is about changing perspective, changing from one basis to another. But the advantages to that are very much like the advantages of going back and forth between different ways of thinking about the same ideas in linear algebra. Whether we're thinking algebraically, geometrically, in one basis or another basis, in terms of a linear map or its matrix representations, and so on and so forth. All right, so we will move forward with these two properties in our toolkit, and our next order of business is to answer the very important question: if fancy A and fancy B are bases of the same space, and V is a vector in that space, if we know V's A coordinates, how do we find V's B coordinates? So this is a problem of translation. We have the same object that can be described in two different languages, basis A and basis B. If we know how to describe it in one, we should be able to translate so that we have its description in the other language as well. But how do we do that? Our answer is ultimately going to involve a matrix. We will find a matrix that will take this vector, V's A coordinates, and turn it into this vector, V's B coordinates, so that the translation process will, at the end of the day, simply be a matter of matrix vector multiplication, which, of course, is very nice. It's amazing what matrices can do. We've seen them as geometric transformations. We saw in Chapter 5 how matrices can do the work of row operations, and now we're about to see how matrices can be used to change coordinate systems. But how does it work? Where does this magic change of basis matrix come from? Well, let's begin fumbling towards an answer. To set the stage, let's suppose that basis A consists of vectors A1, A2, and so on up to AN. So we're working in an n-dimensional space. And we'll suppose basis B consists of, you guessed it, vectors B1, B2, and so on up to Bn. Now, our problem is that we've got some vector V, and we know its V's A coordinates. So we know how to express V as a linear combination of these A vectors. So let's suppose that V is C1 times A1 plus C2 times A2, so on and so forth, to Cn times An, where the C1, C2, and so forth are scalars. Those are the weights we attach to the basis vectors to get a linear combination equal to V. So in other words, V's A coordinates are C1, C2, C3, and so on up to Cn. Okay, now the stage really is set, and we are faced with our dilemma. How do we go from this representation of V as a linear combination of the A vectors to a linear combination of V as a representation of the B vectors? We want V's B coordinates. Well, after staring at this equation for a while, we might think, well, look, I'm after V's B coordinates. All I want to do is take my raw vector V and slap these brackets with the B subscript on it. And I can do that as long as I do that to both sides of the equation, as any elementary algebra student knows. So if I do that, we get this statement. V's B coordinates, now that's the thing I want, are the B coordinates of this long linear combination. Now that might not seem very helpful, but it is, thanks to this stuff we discussed earlier. That act of ripping the coordinates from a vector is itself linear. It preserves linear combinations. So that means that this stuff is equal to this stuff by linearity. We can break this into n separate pieces by this first property, and then we can pull all of the scalar multiples out by this second property, the net result being this stuff. And that is how linearity properties work in general. Okay, so now we have that the thing we're after, V's B coordinates, is equal to this strange expression. Does that help us? Oh, yes, it does, because now we have the thing we want as a linear combination of vectors. And I can take any linear combination of vectors and rewrite it as matrix vector multiplication, right? That's the definition of matrix vector multiplication. The entries of the vector become weights for the columns of the matrix. Read this equal sign right to left, and you'll see that right away. And I'm running out of room here at the climax. So now that we've used this ladder to climb up onto a platform, let's throw it away so that I can clear out some space. That's better. Anyway, we have that V's B coordinates are given by this matrix vector product. But let's think about that vector. We know what that vector is. The entries in that vector are V's A coordinates. So that means we could rewrite this stuff as this same matrix times this vector, the vector of V's A coordinates. So now I've shown that V's B coordinates are given by a certain matrix times V's A coordinates. Well, that's the sort of thing we were looking for. Something that turns V's A coordinates into V's B coordinates. That was our goal. So our process of fumbling towards an answer is nearly complete. We just need to think about a good way to describe all of this stuff instead of having all these bristly symbols around. It will probably help if I collapse these intermediate steps and bring our last expression up to the top. As I said before, this matrix converts the A coordinates of a vector into the B coordinates of a vector. So we call this guy the A to B change of basis matrix. It does exactly what its name suggests. And now let's look a little more closely at this change of basis matrix. We know its columns. Its columns are the vectors in basis A. Those are the A vectors, but we have expressed them all in B coordinates. And that is the takeaway here. We have established the following theorem. If A and B are bases of a vector space, then the A to B change of basis matrix is the matrix whose columns are basis A's vectors expressed in basis B's coordinates. Let's box up our hard-won spoils of war, clean up the battlefield, and bring home our treasure. All right, now that we have established this, let's do a concrete example. Let's work in R2 with the standard basis, which I'll call E, and another non-standard basis, which I will call B. And I've drawn its two vectors, B1 and B2, so that B1's coordinates relative to the standard basis are 2, 1, while B2's coordinates relative to the standard basis are 1, minus 3. Let's play with these two bases, and in particular, let's find the change of basis matrices that we can use for converting between bases E and B. Matrices plural because there will be two. There will be the B to E change of basis matrix, and there will be an E to B change of basis matrix. So let's begin our solution. The B to E change of basis matrix is something that is very easy to write down, because according to our theorem, its columns will be the vectors in basis B expressed in E coordinates. And that's exactly our given information here. Here we have the first vector in basis B expressed in E coordinates, in standard coordinates, which are 2, 1. So that becomes the first column of our B to E change of basis matrix. Its second column is given by B2's standard coordinates, which are going to be 1, minus 3. And now we have our change of basis matrix. That was easy. Let me give this a name. Let's call it C for change of basis. And now that I have a symbol for this change of basis matrix, I'm going to attach some unofficial, non-standard notation beneath it. This is just some chicken scratch that I'm putting below the symbol for the matrix. I'm putting it in parentheses to signal that it is not really officially part of the notation, but it's something I use to keep things straight in my mind. This will become more important as we go on. It's simply reminding me quickly that what this matrix does is it changes coordinates from basis B to basis E. One reasonable question you might ask is, well, why do you have the arrow running right to left? I mean, why not write it as B gets changed to E, left to right, as we normally write? Well, you will see very soon why it makes sense to write it in this direction. It's related to the fact that when we multiply matrices, we are composing linear maps, and ultimately we are reading those right to left. But more on that in good time. But let's get back to the problem at hand, which was to find the two change of basis matrices for converting between these two bases. We already know the B to E change of basis matrix. It changes coordinates from basis B to basis E. If we invert that matrix, what we will get is the matrix that undoes that action, that changes coordinates from basis E to basis B. So to find this latter change of basis matrix, all we have to do is invert the matrix we already have. And that's very easy since it's a 2 by 2 matrix. We have that simple inversion recipe. We start with a scalar factor, 1 over the determinant of the matrix we're inverting. And the determinant here is minus 6 minus 1, so minus 7. And then we have a 2 by 2 matrix that comes from this one in a two-step process. The two off-diagonal entries are going to be negated, and the two entries on the main diagonal simply switch places. And that's that. Now we have our E to B change of basis matrix. And since I introduced this scratchwork notation here, I'll include it here too. What C inverse does is change coordinates from basis E to basis B. And of course, if you want, you can do the scalar multiplication here and push the minus 1/7 into the matrix like so, but it's actually much nicer to have that minus 1/7 factored out so that these entries are all whole numbers. At least if, like me, you like to avoid doing fractional arithmetic where you can. So I'm going to go ahead and erase that stuff. Okay, we have come up with both change of basis matrices. Let's put them to use just to see how they work in concrete cases. So here's a question. If V is a vector such that its standard coordinates are 3 minus 1, what are its B coordinates? Now, before we compute anything, let's make sure you understand what's going on geometrically. We have a vector whose standard coordinates are 3 minus 1. So that would be a vector something like this. 1, 2, 3 over and 1 down. And we'd like to know what this guy's B coordinates are. Where does this point, in other words, lie on the B grid? How many B1 steps and B2 steps do I have to take to get there? Well, let's compute the answer and then make sure it looks fairly reasonable on this one. I mean, if I had to guess just based on my bad picture, it looks like probably we'd have to take a little more than one B1 step and less than one B2 step. So the coordinates might be something like something slightly greater than 1 and then something close to a half. Who knows? Well, we know because we can find out. We've got this vector's E coordinates. We want its B coordinates. This is a job for the E to B change of basis matrix. That is what it does. Solution. V's B coordinates is something we can get by taking its E coordinates and hitting them on the left with C inverse, because C inverse is the E to B change of basis matrix. And again, if I put my little scratchwork notation in here, this may seem clearer. Working right to left, we start with something in E coordinates. We throw it into this machine, which translates E coordinates to B coordinates, and we're going to end up, of course, with something in B coordinates. So now all we have to do is crank out the specifics. In this case, C inverse, we know, is this matrix. Vector V's E coordinates are 3 minus 1. That was given to us. And when we compute this, I'll just leave the minus 1/7 to wait in the wings, and we will take care of the matrix vector multiplication, which is going to be minus 8 minus 5. I will do this scalar multiplication because it will be easier for me to grasp the geometry that way. And lo and behold, we have our answer. And yes, this corresponds to roughly what we thought it would be. V's first B coordinate is a little more than 1 1/7, and V's second coordinate is a bit more than a half, 5/7. Good. While we're here, let's do a second question concerning the same setup. If vector W is 10b1 plus 5b2, what are its standard coordinates? Well, once again, this is easy. We are given, in a slightly different form, but we are given its B coordinates because we've expressed W in terms of the B basis vectors. So W's B coordinates are 10, 5. Now we want to know the E coordinates. We know how that works. W's E coordinates are the result of taking its B coordinates and hitting it with the appropriate change of basis matrix. In this case, that is going to be matrix C, because that is our B to E change of basis matrix. So we start out with B coordinates, run them through the machine that changes B coordinates to E coordinates, and of course we come out with E coordinates. So now we just have to crank this out. Here is matrix C, and W's B coordinates, we said a moment ago, are 10 and 5. So doing this multiplication, we get 25 minus 5. And that's that. We have the standard coordinates of our vector W. Now that vector doesn't fit neatly into this tiny window I have drawn here, but we can probably see that it's fairly reasonable anyway. I mean, vector W was 10b1s plus 5b2s. Well, that's going to take us 10b1 steps, 1, 2, 3, way out here somewhere, and then 5b2 steps. It looks like it's going to take us probably just a little south of the x-axis. So we end up with a high value for the first coordinate in standard coordinates, and a much lower one relative to it, and negative for the second one, and that is indeed what we have. So this checks out nicely with our geometric sense of what's going on. All right, I've run out of room, so maybe it is time to look at a new example altogether. Example 2. Let's work in R3 this time, and to make things a little more interesting, let's not consider all of R3, but rather a subspace of R3. Let's look at the plane through the origin, whose equation is y equals z. This is a two-dimensional subspace of R3, and let's consider two different bases for this space. Let's start with basis A, which consists of two vectors A1 and A2, and let's suppose that their standard coordinates in R3 are given by 0, 1, 1, and 1, 1, 1, respectively. Before we move on, let's verify that these two vectors do in fact constitute a basis for this subspace. First, do they actually lie in the subspace? Yes, they do, because the subspace is defined by the equation y equals z, and that equation holds for A1 and A2. In both cases, the y and z coordinates match one another. So these are two vectors that lie in this two-dimensional subspace, and they are obviously linearly independent because there's no way to scale A1 and come up with A2. Because whatever scalar you consider, when you multiply it by 0 in that first component, you're not going to get 1. You will only get 0. Two linearly independent vectors in a two-dimensional subspace necessarily span that subspace, so yes, this is a basis. I will move it over a little bit so that I have room for basis B. I've drawn its vectors on the picture. We'll call them B1 and B2, and let's say that their standard coordinates in R3 are 2, 1, 1 and minus 1, 2, 2, respectively. Again, it's easy to see that these do in fact constitute a basis for the subspace. Both of these points lie in the subspace, because in both cases the y and z coordinates are equal. Moreover, these two vectors obviously are not scalar multiples of one another, so they are linearly independent. Two linearly independent vectors in a two-dimensional space means that they generate a grid that fills the entire space, so they are linearly independent, and they span the space. Therefore, they are a basis for the space. Anyway, now that we have these two bases, I will propose the expected problem. Find the A to B change of basis matrix. And of course, once we have that, all right, so how do we solve it? As usual, all we really need to do is keep our wits about us, bear in mind the one relevant theorem about change of basis matrices, take care in what we write down so that we can keep track of where we are in our own thought process, and then just follow our noses to the solution. If we understand everything up to this point, we'll have no problem coming up with a solution. So let's see. Our theorem tells us what the columns of the A to B change of basis matrix will look like. They will be vectors A1 and A2 expressed in B coordinates. Now, unlike in our previous example, those aren't given to us right here. We have A1 and A2 expressed in E coordinates, but not in B coordinates. So how are we going to find such a thing? Just think about it. Take it one piece at a time. The first column will be vector A1 expressed in B coordinates. So in other words, the first column of the change of basis matrix can be found by solving this equation, and we want to solve that for the scalars C1 and C2. Those are the weights we have to put on the B vectors, B1 and B2, that will allow us to get A1 as a linear combination of them. Hopefully this makes sense so far. It comes straight from our theorem. Now we have to actually find those scalars. Well, how are we going to do that? We can rewrite this equation in a form that will be easy to work with. Whenever we have a weighted sum of vectors, of course, we can rewrite that as matrix vector multiplication. So this equation becomes this new equation. Vector A1 is equal to the matrix whose columns are B1 and B2 times the vector whose entries are C1 and C2. And now you should start feeling more comfortable, because you could say, oh, well, I know the coordinates of vectors A1, B1, and B2, so I can just pop those in, rewrite all this as an augmented matrix, and go to town with Gaussian elimination. And that's true, but I want to pause here for a second, and before we rush into the solution, I want to lift up the corner of the rug and show you something that I swept underneath there. Yes, we can stick these coordinates in for A1, B1, and B2. But strictly speaking, if we're going to do that, what I would really need in this equation is not just A1, the geometrical vector, but A1's e-coordinates, and B1's e-coordinates, and B2's e-coordinates. Strictly speaking, am I able to do that? And you might think, well, sure, if they're all in the same basis, which is what we're pulling from, they're all e-coordinates, and that in fact is true. But if I wanted to justify that more carefully, and we might as well do that once, we could do so as follows. Go back to this step. Everything looks great here. But since we're ultimately going to be working with the e-coordinates of these three vectors, let's rip the e-coordinates from both sides of that equation. This right-hand side can be simplified by using those linearity properties of this coordinate operation we discussed earlier. When we apply them, this right-hand side becomes this stuff, C1 times B1's e-coordinates plus C2 times B2's e-coordinates. Now this equation looks much uglier than the one we started with because of all those brackets and e subscripts. But we're trying to be careful once so you see what's going on under the hood. I can now expand the right-hand side here, just like we did before when we were acting a little more casually, and say, well, I've got this linear combination of vectors, so I can rewrite that as matrix vector multiplication, and what I end up with is this stuff. A1's e-coordinates are equal to the product of the matrix whose columns are B1's e-coordinates and B2's e-coordinates times this vector whose entries are C1 and C2. And now we see that yes, we can just take the e-coordinates of those three vectors and pop them into this and get what we want. And there's no question about, was that a legal move? It's definitely a legal move. You don't have to go through all these shenanigans with the brackets and subscripts every time you do something like this, but you should recognize that it can be done to justify our actions. Anyway, once we make those substitutions, we get this equation. On the left, we have the vectors 0, 1, 1. On the right, we have the matrix, whose columns are 2, 1, 1, and -1, 2, 2, multiplied by the vector C1, C2. I'm going to clear out some clutter, like so, and we know how we can proceed from here. We can rewrite this as an augmented matrix, and if you put it in reduced row echelon form, I'll leave it to you to show that you come up with this. And from here, we can read off the solutions to our system. These columns correspond to the unknowns C1 and C2. So the first row tells us that C1 plus nothing is 1/5. And the second row tells us that nothing plus C2 is 2/5. And the third row conveys the exciting news that 0 is equal to 0. So we have just found that C1 is 1/5 and C2 is 2/5. And that's good news, because now we have solved this system whose solutions give us the first column of the change of basis matrix that we are looking for. And if we call this matrix C, then its first column is 1/5, 2/5. And if you understood the whole argument that led to this first column, then you are in great shape, because the second column, of course, is obtained the exact same way, except you make the obvious changes. Namely, the second column of the change of basis matrix can be found by solving the equation that will give us A's second basis vector in terms of the B vectors. So in other words, we have to write A2 as a linear combination of B1 and B2. And by the same shenanigans we went through last time, this leads us to a system of linear equations, which I can write as a augmented matrix. After the usual Gaussian elimination, we come up with this, and bearing in mind that the columns correspond to the unknowns C1 and C2, we read off our solutions. C1 is 3/5 and C2 is 1/5. Those will therefore be the entries of the second column of our change of basis matrix. So at the end of the day, our change of basis matrix C looks like this. Or if you prefer, you could remove 1/5 from all the entries so that you have the scalar 1/5 times the matrix whose columns are 1, 2, and 3, 1. Good. Well, let's see. Should we do anything else with this example? Oh, maybe very quickly. Now that we have the A to B change of basis matrix, let's find the B to A change of basis matrix. That, of course, is going to be the inverse of C, and we could invert this matrix, of course, using the usual formula for a 2x2 inverse, and that would be perfectly fine and would take just a few seconds. But I'm glad that I factored this fifth out here, because it gives us an opportunity to think about how that would affect our calculation of the inverse. I mean, let's just do a little scratch work over here in the dungeon. If I have a scalar multiple of some invertible matrix M, what can I say about the inverse of C times M? Is this one of those cases where I can just pull a constant through the symbol? Or should this be something like the inverse of C, like 1 over C times the inverse of M? Well, you don't have to guess, just think about it. In fact, there's several different ways we could think about it. First, let's think about it geometrically. What does scaling a matrix do geometrically? Well, it multiplies every entry of the matrix by that constant. So it's like every column of the matrix is getting scaled by that constant. So whatever the matrix did originally, think of it as changing the standard basis vector into some new basis, throwing the C on at the end, stretches all of those basis vectors by an additional factor of C. So to undo the effect of M followed by this scale, we'd need to not only undo M, but undo the scaling factor as well, which means that if we multiplied all the vectors by 19, we would then need to divide them all by 19 to bring them back down. So that's one way to think about it, but let's think about it algebraically too. We've got some matrix, C times M. We are trying to multiply it by something to get the identity matrix. That's what it would mean for this thing to be CM's inverse. Well, a little thought shows that 1 over C times M inverse will do the job, because when I multiply all this out, we know that scalars can be pulled through multiplications like this, so that all this stuff on the left could be written as C times 1 over C times M inverse, and of course C times 1 over C is just 1, so that factor disappears, and M times M inverse, of course, is the identity matrix. So yes, this all ends up multiplying out to give us the identity matrix, which means that 1 over C times M inverse is, as we said before, the inverse of C times M. Anyway, that was just a brief side discussion, since it was staring us in the face. You don't have to use that fact here, but if we do, we could say that C inverse is the reciprocal of this scalar factor, so 5, times the inverse of this 2x2 matrix of whole numbers. And that's easy enough to compute. To invert this guy, guy, we find its determinant, which is 1 minus 6, so 1 over minus 5. The off-diagonal entries sprout negatives, the main diagonal entries change places, and this all works out to this matrix, whose columns are -1, 2, and 3, -1. So for example, to finish this off, let's say we wanted to know vector B2's A coordinates. Well, here's B2. I'm guessing this is going to end up being something like, well, we'll have to take a positive number of A steps, A1 steps that is, and then eventually we'll take some negative A2 steps. So I think we're going to get a positive followed by a negative. Let's see how it works out. This is what we want, and we know that to get a vector's A coordinates, we could start with its B coordinates, if those are known to us, and then hit that vector with the appropriate change of basis matrix, which in this case is C inverse, because as we said, that is our B to A change of basis matrix. So it looks like everything works out when we stare at our subscripts. We start with a vector's B coordinates, feed it to the matrix, which changes B coordinates to A coordinates, and so, no surprise, on the other side of the equal sign, we get something in A coordinates. Let's carry out the computations. C inverse, well, we already said what that matrix is, but now wait a second. What are the B coordinates of vector B2? Well, that's obvious if you think about what is meant by coordinates. Here's vector B2. To get to that vector, how many B1 steps do I have to take and how many B2 steps do I have to take? Well, it is B2. So I take no B1 steps and one B2 step. So B2's B coordinates will be 0, 1. And when we work out that matrix vector multiplication, we get no copies of the first column, 1 copy of the second column. So therefore we get 3 minus 1 for our A coordinates of B2. And that matches up with our intuitive picture of the geometry. To get to B2, we said we were going to take some positive number of A1 steps and then some negative amount of A2 steps. So that's what we had, 3 and then minus 1. Good. The last thing I will mention is just to observe how, even though the ambient space in which we were working here was R3, which meant that it was possible to take all these various basis vectors and write them with 3 components, because we could think of them as vectors in R3, so we could talk about how to reach them in terms of the standard basis vectors of R3, I, J, and K. Even though we could do that, that is not really, ultimately, the best way to think of stuff happening in this two-dimensional subspace of R3. All we need is a basis for that subspace, and everything starts to look two-dimensional algebraically. That is why, for example, our change of basis matrices between two bases of that subspace were 2 by 2 matrices, not 3 by 3, even though our vectors in some sense live in R3. And when we describe any individual vector in that two-dimensional subspace, we only need 2 components to describe it. We don't need 3. But what those 2 components are depends on which basis of the subspace we used. For example, this vector B2, if we describe it in terms of basis B, it was simply 0, 1. If we describe it in terms of basis A, another basis for that two-dimensional subspace, it's 3, minus 1. But if we describe it in terms of E, the standard basis for R3, well, now it's got 3 components, minus 1, 2, and 2. All are adequate descriptions, but typically speaking, if we can get by reducing the number of dimensions, by thinking of it in terms of a basis for its own space, we are better off. All right, that's that. In the next video, we will move deeper into Chapter 6 and discuss how not only the components of a vector change when you change your basis, but the entries of a matrix that describe a linear transformation will also change. Understanding that will depend heavily on understanding the material in this lecture and the corresponding section of the book, so please do work on getting that down. All right, until then, adios.